Okay, our next section in Chapter 9 is on similar triangles and indirect measurement. And similar triangles have a very particular definition when you're talking about geometry. One definition of similar triangles are triangles with the same shape but not necessarily the same size. We'll talk more specifically in a minute about a geometry definition. But what do I mean by this? Let's say we're to draw one triangle here, call it ABC, and another triangle here. I'm going to make it bigger. I'm going to call it DEF. And if I tell you that this angle is the same measure as this, and I put a little curved arc mark there to show that, and that this angle is the same as this one, and then of course this one will be the same as this, because since all the angles have to sum to 180, if two of the angles in one triangle are the same as two of the angles in the other, then the third angle will have to be the same because they both have to add to 180 degrees, right? So it turns out that these two triangles, triangle ABC, is similar, and there's a specific symbol for that, looks like a sideways S, similar triangle to triangle DEF. They are the same shape, but not necessarily the same size. So this means is similar to, okay? And in similar triangles, corresponding angles are what we call congruent. And I'm going to define what congruent means. Congruent in geometry is just another word for same measure. They're the same size. So if two angles are congruent, that means that they have the same measure. If two line segments are congruent, that means they also have the same length. It's just the geometry term for same measure. Okay? So I'm going to write down what I said before, which is in similar triangles, corresponding angles are congruent. So in similar triangles, corresponding angles are congruent, and that's shown by the same number of arc marks. And let me just remind you what I was doing there. Oops. I'll just redraw what we had before, the ABC, the DEF. The fact that A and D have the same measure and they have the same number of arc marks, and B and E have the same number of arc marks, those are two arc marks, and then the third angles also have the same number of arc marks. Those indicate which are the corresponding angles. So when you name the triangles being similar, you want to name them in the same order as their corresponding angles. So for instance, before I said triangle ABC was similar to triangle DEF, I could also name them differently. I could have called it triangle CAB. If I call it triangle CAB, though, I have to name the other one. When I'm naming the similarity, I have to name them in the same corresponding order. So you have to figure out what angle matches with angle C. So you have to see, okay, this one has 3 arc marks, so I have to look at the other triangle and say, oh, okay, this angle has 3 arc marks. So I'm going to label the first vertex that I'm going to label is angle F. Okay, so C matches with F, then A, which has 1 arc mark, matches with D, and then B, which has 2 arc marks, matches with E. So if I name the first triangle CAB, I have to name the second one FDE. I have to name it in corresponding order of letters. Another important aspect of similar triangles, and remember these two triangles are similar, not only are all the corresponding angles congruent, but all the corresponding sides are in proportion. Let me write that. So here we are. In similar triangles, all the corresponding sides are in proportion. So what do I mean by that? I mean that if I take side AB, and notice that that's these two letters, the second and third letter, so those must correspond to side DE. So AB over DE is in the same proportion as, let's say, AC. Now let's figure out which side matches with AC. So AC are the first two letters, so they have to match with the first two letters here, FD. AC over FD, which correspond to BC over EF. So these are the two very, very important concepts about similar triangles. Corresponding angles are congruent, and all corresponding sides are in proportion. So how do we use this? You can use proportions, for instance, to determine measures of sides of similar triangles when some measures are known and some are not. Okay, so here's an example. Let's say triangle CAT is similar to triangle DOG. Triangle cat is similar to triangle dog. And you're asked to find AT. So this is this is the segment you're trying to find. From A to T. This one right here. Okay? So we are given some information. We're given some side lengths, but we're not given AT. So first of all, we know what the corresponding sides are. For instance, side CA, which is the first two letters here, have to be corresponding with side DO. So this side CA corresponds with this side DO. And since we know that corresponding sides are in proportion, we can make a little ratio. We can say 8 meters is to 4 meters and then we want to know what side is this. This is side AT, right? So side AT, for the second two letters, those must match or correspond to side OG, this one right here. So AT and OG must be corresponding sides. So another ratio we can set up is X over 10 meters, right? We can ignore the meters really for now and just put it in at the end. So this is what we mean by corresponding sides are in proportion. That means you can set up ratios, set up a proportion to find the missing side. Now in this case, you're going to want to cross multiply. So you get 8 times 10, which is 80, equals 4 times X. And then you're just going to go ahead and divide both sides by 4. And you'll get X equals 20, and remember, that's 20 meters. So that's the missing side AT. Okay, I want to walk with you through a problem that's in the book. So why don't you pause the video and go get your textbook and open it to page 473. We're going to look at number 5. Now on number 5, there's a little picture. I haven't drawn all the aspects of the picture, but sometimes it's useful to use properties of similar triangles to find measurements that are difficult to measure directly. And in number 5, there's I think different cities, and it might be a little bit hard to find. All of these measures are in kilometers. I didn't put kilometers in just because it's, I didn't want to busy up the picture. Sometimes if you want to measure, for instance, the distance across a lake or the height of a tree that's too tall to climb and measure directly. So these are things that are called indirect measures, and we're going to do that. We're going to do more indirect measure, another problem in a second. So in this problem, you're given the similarity. So you know which vertices match up with which. So what you're given are 3 sides, and you need to find a fourth measurement. So you need to know which sides match with which. So this side, AB, right here, are the first 2 letters here. So that, if we're talking about these 2 triangles, this one down here and this one up here, side AB, which we'll darken in right here, the first 2 letters, has to match with the first 2 letters here, so it has to be side ED. So let's say we say 18 to X has to equal, and we have to go in the corresponding order. So if we did this large triangle on the numerator, we have to do the large triangle of the other side, so that we've got side BC, which is the second 2 letters, have to correspond with the second 2 letters here, DC. So we have to write 6 over 2. In other words, we just have to stay consistent. I could have, if I had wanted to, I could have written X over 18, but then I would have had to have written 2 over 6. So you can do either way. When you cross multiply, you will get the same answer. Let's go ahead and cross multiply. 18 times 2 is 36, equals 6x, and we're going to divide both sides by 6, and we get x equals 6, and we have to remember that's in kilometers. Okay, on page 473, number 6, I've drawn a very crude picture here. I'm not an artist, I'll admit that. it says at the same time a 10-foot flagpole, so let's actually label that. That's 10 feet high. A 10-foot flagpole casts an 8-foot shadow. So what we're talking about is the shadow, which would be on the ground. Okay, so this is what they mean by the 8-foot shadow. I didn't draw the shadow, but you can imagine a shadow is on the ground. And then it says a nearby tree casts a 40-foot shadow. I think I might have drawn this incorrectly. I think the tree is actually supposed to be taller. Let's make the tree taller. Let's see if I can find the right color to make this. There we go. Let's try that again. Okay, the tree is going to be up here. And it's going to have some green leaves on it. We'll make it just have a lot of green. There we go. Okay, so the shadow of the tree, let's erase this earlier one. I guess I didn't read close enough in advance to draw it correctly the first time. So let's see where that 40-foot shadow is going to be. That's going to be there. And the question is, how tall is the tree? So again, these two triangles are supposed to be similar. We assume that both of these are right angles here. And we can assume that we can kind of guess. If we call the height of the tree h, we can guess that the 10 foot and the height of the tree, the height of the flagpole and the height of the tree are both, those are corresponding sides. So you're going to say 10 over h equals, and then this side is going to correspond with this side, 8 over 40. And then you can either reduce first and then cross multiply. So if we did that, we could reduce this to 1 over 5, and then you cross multiply and you get 1h equals 50. So you get the height of the tree is 50 feet. So that's a way that you can use indirect measurement to measure something using similar triangles. It might have been harder to actually measure with a tape measure or something the height of that tree, because it would be hard to climb the tree.